How about now? There we go. I thought I checked everything, and I didn't. Here we go. Perfect. Hope you're doing well. Thanks for joining me on this adventure into Zephyr. Here we go. And this week was a suggestion by someone who had joined last week, and he was more interested in getting into low power. So getting below 5 microamps of power any way possible. I'm assuming as like kind of low power state, kind of standby, active standby, deep sleep. So we're going to talk about kind of two modes that that are available in this guy right here. I'm gonna pick it up real quick. If I can pick it up. This guy right here. So it actually has two low power modes that I threw in on the hardware side, and also works very much so on the software side as well. So we're going to talk about that, talk about my kind of experience. It's very similar to how I designed the NF9160 Feather in terms of the original features that I had in mind. So we'll kind of jump over that. We'll actually go through everything and then go through an example showing kind of the difference in power using one of the tools here as well. So we will do it all. And here we go. So if you haven't already, hit that like, hit subscribe, and get notifications when these videos go live. So the question was from Thiago, how to reach ultra low power less than 5 microamps. So let's do it. We're going to review some of the easiest way to reduce IQ or quiescent current. Hardware design is huge. It's kind of like the 75% of it. Maybe less than that. 50%. The other 50% is software, because software can be tricky sometimes. Big thing is just understanding what you can do in Zephyr, what's already done for you, is also pretty critical. And then having the tools to make those measurements is also very important for us, because without those tools, we wouldn't be able to figure out what's going on. In terms of a hardware situation, so I take a look at all the components that I can think of when I'm doing my search, and especially if I'm doing anything low power. So I've been designing low power for, I don't know, almost for a while now, and I've lost track. But the big thing is kind of poring over the data sheets, making sure that you're going to be getting the performance you want, the low power that you want. Then you can start thinking, okay, how can I hack this a little bit more to get even more low power? Things like shutting down power supplies, disconnecting them, using load switches, things like that. Those are hacks that you'll kind of go way beyond just like putting it apart and kind of using the reference diagram. So I did that it was more of a hack on the NF9160 Feather. What the cool thing about the new one is that it uses the NPM 1300. So we'll talk about that a little bit more. But things like other things you want to consider is like, what's the sleep current of the processor? That's pretty critical, especially if you want to keep it on in kind of an semi-active state. So the PSM sleep floor for the NF9151 is 2.7 microamps. So some things are just unavoidable, especially if you want to keep it running for, and keep it active. I know there are other processors out there that might be lower active current, but there are kind of trade-offs and multiple things at play going on. So speaking of trade-offs, there are, you have to think about your features, but also the power efficiency and what will be best for your application. Another thing to keep in mind is board space. So having multiple different discrete ICs that are doing different things, and PPT, a charge controller, switching power supplies, some load switches, all this stuff adds up into space, and sometimes you run out of said space. So you can see here on the bottom, that chip right there in the middle, that is the NPM 1300 along with its two switching regulator. You can see the two inductors and some of the other supporting circuitry, filters, things like that. So it is all there on the back. And in this case, I chose the, even though this guy does use a little bit more current, I think having some of the features, and we're going to jump into those features, is pretty critical, especially for these low power applications. And having the ability to turn off and have control over the power supplies is kind of cool. So you'll see why I use it in a second. So the biggest thing is, okay, quiescent current for the power supplies is pretty darn good. Most cases, I mean, compared to that TI chip, it's still high in quotes. But there are some switching power supplies out there that use anywhere between 10 to 100 to 200 microamps. So having something that's less than a microamp that's giving you a stable power to your chip is still pretty good. So, but the thing it does also is you have battery and load control. So there's a built-in load switch essentially. So you can switch over to, it'll automatically switch over to using the USB instead of battery. Things like that. It's got a built-in charger, dynamic switching. So, for instance, you can turn on and off the power supplies and the load switches using software and also input pins. So it has a bunch of GPIO input pins you can set to control. You can also modify the output voltage. So you can set the output voltage for both of the LDOs or the switching regulators. I believe the other guys are, it also has two LDOs / load switches. So those are also adjustable, I believe. And you can change those. You can set them with a resistor, but you can also adjust them in runtime to whatever you want. So for instance, my board runs on 2.7 volts by default because you can get a little bit lower and everything will run okay, but you can actually bump it up to 3.3 if you have compatibility issues, things like that. So, and another really cool feature, and this is what I kind of did on the Enterprise 160 at first, was allowed an RTC, some type of clock, fairly accurate clock, to you put everything to sleep, you turn off the power supply, and then you use it to wake up in some time in the future. So you can think of this as a way to, it's great for periodic measurement, like low power periodic measurements, where maybe you only want to wake up like once or twice a day and take a measurement and go back to sleep. This is the case where you're going to get sub microamp current draw, and you're going to wake up, you're going to do your thing and shut it off, and it's just, your battery life is going to be pretty fantastic. So you can do this all discreetly, you can do it with a bunch of different parts, but if you have a tiny little board, that's kind of the thing you're battling against. So there's some advantages and disadvantages to it. So here's kind of like the schematic snippets of how things are. There are two switching power supplies. You can configure them as you wish, but I have one that's kind of powering everything, and the accelerometer, external flash, everything like that. The other one is powering kind of the USB domain items, which is the RP2040, the flash for it. The cool thing is, like, hey, I can turn it off if I want to, if I disconnect from USB, but I can always keep it on. I can keep it on and turn it back on. It's really up to you and your application. You could load a different application to the RP2040 and kind of use it as another processor on the side if you wanted to. But that processor is not, so comparing the two processors, or a Nordic chip to the Raspberry Pi, the RP2040 is not power efficient. So when it comes to, if you want to leave it at an idle, the idle I think is around 200 microamps. I think it's a little bit more last time I measured. So just keep that in mind. And the always on, here you go. As you can see, like external flash, and the everything being on that rail also means, like, hey, you can actually just power everything down, use the deep sleep modes of the NPM 1300, which is cool. And we'll go into that in a little bit. Actually, we'll go into that a little bit right now. Here is some of the code that I kind of mentioned, and for this one is actually allowing you to set the pull downs for both the bucks. So say you want to disable these bucks, you can actually say, hey, I want to set an active pull down when they're disabled. It'll keep things, prevent anything from latching up or floating in a weird state. It'll just bring everything down, turn everything off. I've seen some weirdness where you might turn off the load switch, and then because it's still kind of floating, things will stay active, and then it'll find some weird path back, and everything will continue to stay powered and back powered, and it's not fun, to say the least. So this is kind of a cool thing that they have. This NPM 1300 has a lot of features and it's very cool. A lot of work has gone into it, and it's not perfect, but I'm happy that it's a part of the board that's coming up. So one thing that I put some links to it in the description: the deep sleep sample and the active sleep sample. Both of those utilize the NPM 1300. Oh no, correct me. I will correct myself. The deep sleep uses the NPM 1300 functionality. The active sleep, which is also what we'll be talking about, just uses kind of the functionality in Zephyr and the API calls to make sure everything's low power. And so this is actually, so we're looking at the deep sleep functionality right now, and I just put both of them in here just as an option, just so you could see. But you have the hibernate mode, which you're basically setting a timer, and it's just going to come back in, I believe that's in milliseconds, so it's going to come back in a minute or 60, yeah, so in a minute. And the other option would be, okay, you can use the ship mode, and the way you wake up from that guy is, I believe there's a pin on the board, the enable pin, I believe, and if that one is toggled in a certain way, it'll kind of power everything back up. So ship mode is very common for consumer electronics that go from the factory out. You don't want the device to be using the battery while it's sitting on a shelf for 3 months. So the idea is, if you want to, it's great for keeping and reserving battery life for when it's actually needed. So that's what's handy about that. But the big thing for us, and that's probably the most used feature that I would say if you deploy something in the field, is the hibernate mode. And that's the part where you can disable all the power supplies, and then it'll wake up using a built-in RTC, a low power RTC later on. So this thing's going to be using minute amount of current compared to the normal standard sleep mode. The active sleep sample. So we kind of talked about deep sleep, using that functionality where you're disabling everything. You're turning everything off, basically. You're turning the power off. On the active sleep side, we have some tools at our disposal in the software to kind of disable high-speed clocks, disable UART at the console. So that's a big thing that people run into, especially in Zephyr, is if you have the UART console for debugging, you have the output. It's usually RX only, so our transmit to whatever is fine. But if you have the receiver on the chip turned on, it takes about 1 milliamp. So this is for Nordic chips. Might be different for other ones, but if you're not debugging or actively sending something to the chip, if you disable the receiver, you'll save a lot on current. In this case, you can just completely disable it if you want, so I'll show you that. Using the power management API to disable things like flash, accelerometer, it does draw a minimal amount of current, but you can turn it off or reduce the sampling amount, especially if you're not using it. So things like that. So we'll take a look here. This is the ones for accelerometer. We're basically using the sensor API to actually disable the sampling on the LAS2DH12TR. And originally, an older version of the driver would not allow you to set it to 0, but newer ones allow you to set it to 0. And setting it to 0 basically says, hey, turn this thing off, put it to sleep. One of the important power management APIs is the PM device action run. This is for newer versions of Zephyr, and you basically say, hey, I want the device that I'm targeting. So you need to pull the device first. You're going to do a device DT get. And then you say, hey, I want to run this action on it. So it could be wake up, suspend, whatever. In this case, we're suspending it. So we're basically turning the console all the way off. So it will not send any more text. It will not be able to receive anything. I like doing this conditionally for any application that I might need to log into the console and issue commands occasionally, but for 99% of the time, I wanted to disable the console so it doesn't draw extra current. Another thing is on the ARF 9160, might not be so much an issue on the newer one, but I do enable the high-speed clock for different purposes. So there is a clock API, but I just go straight to the register and just disable the high-speed clock using that command. So there it is on the bottom. Here are some so that you can actually use the regulator API in Zephyr to control the NPM 1300, which is pretty cool. I'm a big fan of using the drivers or the pre-existing system drivers as much as possible instead of just like writing manually to a device. It's kind of nice. So there is a regulator is enabled, so you can check if it's enabled. You can disable it. So regular buck2 is the buck converter for the USB side, so the one that is powering the RP2040. So it's just saying, hey, I don't want it. Turn it off. And then this is the pull downs again, so we don't have to talk about that much. I must have copied and pasted it from earlier. Here is like the we're using the power management API again for the SPI NOR flash. So it does have, so there is a mode where you can basically say, hey, I want to use the sleep mode. It's basically a kconfig that you can say, hey, I want to use this mode to sleep when in idle. And the problem with that is that I've seen is when you enable it, every time you do any type of operation, it kind of assumes you go to idle immediately. So it wakes up, has to wait and get started back up again, does the operation, then goes to sleep or turns off, and then goes to sleep and does this thing, and then just does that over and over again. And it slows flash operations down a lot. So if you do find yourself using external flash, then consider manually controlling when the flash is on and off. That will probably save you a lot of headaches. Just a pro tip. And like this is just the initialization order of kind of how I was doing everything. And those are kind of all the steps that you saw, minus some like GPIO setups and things like that. These are some of my favorite tools. So I've talked about them before. They're very well known, and I don't know how I'd be able to do what I do today without some of these things. So I started out with a microcurrent gold. It's pretty cool. Let me see. I just have it. I have it on my desk. If I just switch it over there. So built this thing from scratch. It is open source, which is pretty neat. And it just hooks right into a multimeter, and it allows you to take current settings, different levels, so you can switch it to kind of different ranges. So you can set it to 1 millivolt per nanoamp, microamp, and milliamp. So depending on your needs, it's pretty nice. I have found that if you're measuring kind of low range current, it will affect the circuitry a little bit, and you might get some unexpected results. So that's just something to keep in mind for that particular device. The power profiler, which is also awesome, I have it hooked up here on the desk right now. Of course, I have it plugged in. I'm going to leave it plugged in because that's going to be part of the demo. It's probably my go-to. It's the easiest to use, and it has a built-in power supply, so I don't have to boot up the power supply to my left here. My Agilent HP, whatever this thing is. Yeah, it's an Agilent. And it just makes it a little bit easier. Just like, okay, I just need to make a quick measurement. I just like to see what's going on here. The downside to the power profiler is the sampling frequency is the max sampling frequency is not crazy fast, and I have seen different results between the power profiler and the dual scope. So often the dual scope will pick up more current usage versus the power profiler. So it's just I like running them both just to see if there's any difference, and usually they're about the same. So so this is kind of what it looks like. I will share my screen shortly, and I'll show you guys kind of the differences. Actually, I have to share the power profiler screen somehow. I'll have to figure that out. But we'll program one of the samples, and I can show you like kind of the before and after if I can get it. So this is a measurement I was taking earlier, and you can see you get like an average in the left corner there, bottom left corner. You can see you get a kind of an average that you can use as kind of a guide as to how much current you're using. You can see one of the coolest things that I saw when I first started using these tools is like current isn't just like flat, right? It's something's always happening. There are blips and there are spikes, and you can really see when Wi-Fi turns on or you have an LTE transmission. You really tell when those are happening. It's like you never really thought about it. You're just like, oh, this thing is doing its thing, like 20 milliamps. How does that work? But when you actually see it plotted out over time, you're like, oh, this is kind of these are kind of important things to understand and to design for in hardware and make sure you're able to handle those big spikes. So we'll jump over to VS Code if I can jump here. Oh yeah, it worked. And we'll open an existing application. You have to trust me that I'm actually opening an application. It doesn't show it. I am opening the active sleep sample, and I'm going to edit my build configuration for the Nordic SoC. That's what I want. 9151NS. We're using sysbuild. We're going to build it. View terminal. So we kind of went over this last episode. If you haven't seen the last episode, I kind of went over usage of Interconnect VS Code and how to kind of use it. So, but I'm just kind of breezing through this because we already went over it last week. So feel free to check out the last live session if you haven't already. And it's chunking along here. Thank goodness for a faster machine. Active sleep sample completed. Now let me see if I can change the video capture. Oh, not this one. The window capture to the power profiler. Aha. And I will just adjust this so everybody can kind of see it. So this is the board, the NRF9151 running the test sample. So I have an RGB LED, and that's what those spikes are, is the RGB LED turning on and off. As you can see, for a power situation, low power situation, not ideal. LEDs are probably the worst. You never want to keep LEDs on for a long time, but this is just a test software, so that's what it's meant for. I'm going to jump into the samples, active sleep. So let me jump back. I will jump back to the VS Code window right quick. Oh, it's huge now. Aha. And I will program it. So, and is the 9150 do one. We should have our merged hex file in here. So probe.rs download merged. And I need to remember all the I'll just do this a little bit faster. I don't remember all the command line arguments. The biggest thing is setting the binary format for probe.rs, chip type, and I'm also just going to execute a reset at the same time. So I'll let it do its thing. So this is using the onboard Seamless DApp onboard programmer essentially, and it's programming it. And the cool thing is you can use it for both the modem firmware side and the application side. So if you ever have to if you want to upload your or update your modem firmware, you can do it with the same tools, which is awesome. All right, window capture. Let's do this thing. Sweet. Interesting. It's doing something. But it's not blinking. It's acting like it's blinking, but it's not blinking. Ah, hold on. Not as low as I'd want, as it should be. Maybe because it was. There we go. Getting there. So this is, I had to, I just reset the power essentially to the board. So it was probably angry. It gets, so whenever you program, especially with, make that go away. Whenever you program with over SWD, the onboard hardware peripheral to handle that gets activated unless you kind of power cycle the chip or reset it. It's going to stay active, and that draws an extra certain amount of current. So in our case, just reset it, and you'll have a better representation of how much current your board is drawing. So in an active sleep mode, 10 microamps plus or minus. It depends on temperature, depends on the hardware, you know, have some variances in hardware, things like that. So we just went from a couple milliamps of turning on and off. I think that turning on and off when I had it plugged into USB still was also probably related to the charger. It's probably trying to charge the battery, which is the battery is the power profiler kit. So you get the general idea. So I went from, you know, seeing that to, you know, we can change some things. We can tweak it if we wanted to. We can change and see how it affects the output current, the sleep current of the device, and kind of go from there. So this is kind of like my workflow. I make a change, I load it. I might have to reset it to make sure everything, you know, things are in a good state. Test it and iterate and go from there. So a lot of that's kind of been the discovery in Zephyr, making these samples. Is just making sure that I'm doing all the right things in the API, and just make sure everything's kind of turned off, because sometimes you have things that just stay on. Perfect example is the console. So when you turn them off, you're good to go. So, all right. Let me see if there are any questions. I don't see any questions. 7 people viewing. Hey guys. That is pretty much it for this one. So we'll kind of recap here. Hardware design, 50% of the importance of when it comes to low power. You need to pay attention to key parameters in the devices that you're using. You also need to design your circuitry. You could always design and add in chips that are low current, but if you don't set them up properly, If you have some, a big killer is like different voltages on the same board, you're asking for uh, flow paths that you did not anticipate. So if you have things powered on different domains, you got to make sure the isolation between those domains are good. Otherwise, you are going to have leakages and backpowering and all that type of fun stuff. You can take advantage of just the low power APIs and functionality in Zephyr. I've kind of harped on this in the past, but when it comes to Zephyr, if you have good support in Zephyr, especially from the manufacturer, they are often doing the hard work for you in the background when it comes to drivers. So Nordic has done a fantastic job with their drivers and functionality where a lot of this stuff is already done for you. So I kind of mentioned it in the past, or I had somebody reach out to me and they're like, "Hey, free RTOS, I can just do everything. I have access in the knobs. I can kind of do everything." And in Zephyr, it's one level lower where it's kind of been optimized and done for you, and batteries are included, and really it allows you to just focus on the application. And some people don't like that, and I get it. I like working on the application and just shipping that out the door, and relying on the fact that these drivers are 99% optimized for most applications. So I will say that that's my piece on that. So you have the APIs, you have the functionalities and the hardware to literally go to deep sleep and turn off completely. So that is also another function which is very, very handy, and that's something that I know people are going to go for. They're going to use a lot, especially for these low power cellular operations where, hey, you have something that's sleeping, taking a reading every day, and you really don't want it doing anything else in between that time. So, and obviously there are tools out there. Those are just some of my recommendations. There are tons of other ones out there. There's a plethora of different options. So that's what I got for you guys tonight. And don't forget to subscribe. I sent out an email just to let everybody know this was happening. And also subscribe to the channel and you get a notification there too. So that's it. So if I don't know if I'll be doing a live stream next week. But if I don't see you guys next week, have a Merry Christmas, and see you on the other side. Thanks for joining.